All right, I wanted to walk you through the derivation of the derivative of inverse sine of x, but at a little less than the warp speed when we went through it in class today. So I've got this inverse trig function about which I do not know the derivative, so I'm going to rewrite that as something that I do know the derivative of. I know the derivative of sine, so I'm going to take the sine of both sides of this equation. And since the sine and the sine inverse are inverses of each other, they would cancel each other out and leave you with sine of y equals x. So I'm interested in taking the derivative of this, and now I can because I know the derivative of sine. So I'm going to take the derivative with respect to x of this equation. Now, this sine has a y inside it, so that means there's a dependent variable mixed into the problem. So this is going to require implicit differentiation, which the first step of it is to replace the y with f of x. Then I'm going to take the derivative of this using the chain rule. So the outside function is sine of x. The inside function is f of x. So the derivative of the outside is cosine of x, and the derivative of the inside is f prime of x. So the chain rule says that this is plugged into that, and then gets multiplied by the derivative of what was inside. Now, the derivative of the other side, the derivative of the x, is 1. So I'm going to switch this back to the Leibniz notation because that's a little easier to write with. And I'm going to solve for dy dx. Do that by dividing both sides by cosine y. And then 1 over cosine is secant. Now, I wanted to find the derivative, but I want to find the derivative in terms of x because the thing I started with up here had an x in it. So I want to get the secant of y into something that's equivalent, but with x's. So y originally was inverse sine of x. So I'm going to take that and plug it in for the y. And now we're ready to draw our right triangle. So draw a right triangle because all of trig is based upon right triangles. My angle that I'm looking at is inverse sine of x. And that inverse sine is taking in a ratio of opposite over hypotenuse. X is x over 1. So opposite hypotenuse. And then I would use the Pythagorean theorem to find the length of the other leg. When I do that, that would give me 1 minus x squared under a square root. And then I want to find the secant of that. Well, secant is hypotenuse over adjacent because it's the reciprocal of cosine. So the secant of the inverse sine here would be 1 over the square root of 1 minus x squared. And that is the derivative of inverse sine. You'll need to write that down because you're going to need to memorize it. Now I'm going to do the derivative of inverse cosine as well so you can see what that looks like. Is 1 over the square root of 1 minus x squared, and the derivative of inverse. So inverse cosine of x is what we're trying to get the derivative of. So I take the cosine of both sides, take the derivative with respect to x. This is chain rule. And that y is an f of x. The derivative of cosine is negative sine. The derivative of f of x is f prime. So chain rule says negative sine of f of x times the derivative of what's inside equals, that's the derivative of that side. So then the derivative of x is 1. If I switch that back to the Leibniz notation, and then if I solve dy dx, I get 1 divided by negative sine of y, and 1 over sine is cosecant, so this is going to be negative cosecant of y. Y was originally inverse cosine. So now I'm ready to draw the right triangle. To make it algebraic, So I'll draw my right triangle. The angle I'm looking at is inverse cosine, which takes center ratio of adjacent over hypotenuse, so x over 1. Then I would find the length of the opposite side using the Pythagorean theorem. And I want the negative cosecant of this. So the cosecant is the reciprocal of sine, so instead of being opposite over hypotenuse, it's hypotenuse over opposite, and there's a negative out in front of it. So notice that the derivative of inverse sine is the negative of that.